This video is for Chapter 3, Section 3.4 for the activity set Dividing with Base 10 Pieces. We're going to learn about the measurement and sharing concepts of division and how to model division questions with base 10 pieces. To start off with, we're going to look at our two division concepts. The measurement or subtractive concept is modeled with this picture. How many piles of 3 cards can you make from a total of 39 cards? And you see that I measure off 3 cards for each pile. Measurement, measure off. Then the next concept, the sharing or partitive concept of division, is just illustrated by asking the question, if 39 cards are separated into 3 piles, how many are in each pile? So you can see I've shared the cards evenly into 3 piles. Each question can be answered by really just computing 39 divided by 3, and we in both cases get 13. Here for measurement we get 13 piles, which is right in our question, how many piles? And here for sharing we get the size of the group. 13 in each group, and that's right in the question, how many are in each pile. You can use base 10 pieces too, and if we're going to look at 36 divided by 3, you can model that with base 10 pieces. So in this first picture, we have the sharing concept. We have 36 divided into 3 groups, and in the second picture, we're using the measurement concept. Here we had to trade out all our pieces, and so you can see you could use tiles or blocks or even X's for this. So we measure off 3 at a time here. In both cases, our solution is 12. Here there are 12 piles or groups, and here there's 12 in each pile or group. So for number 1, we just ask you to do 2 such problems, 1 measurement and 1 sharing. Then in question 2, we note that sometimes we have a remainder. For example, when we divide 20 divided by 3, we get 6, and then we have a remainder of 2. So you can just show that in your diagram. You have a remainder off to the side for both the measurement here and the sharing here. So for question 2, we ask you to do a sharing and a measurement problem. These will both have remainders, and show them in the diagram. And again, here you can keep simple sketches, little boxes or X's. Then in question 3, we talk about how division sort of naturally arises in an elementary school classroom. Suppose you have a package of 20 stickers. And here we ask you, so which division concept is it if they want to divide the stickers evenly amongst 5 students? And then we ask, what if we want to give each person 5 stickers at a time? So support your answers with sketches and see if you can explain which setting is which for question 3. Then in question 4, we think about when we divide 36 by 3 in activity 1, our answer was 12, and we got it in 2 different ways. But if you remember from multiplication, we used rectangular arrays quite a lot. And so we want to use that same concept here. We're thinking about the dimensions of rectangles. So when we think about 143 divided by 11, we want to maybe think about a rectangular array. So in both cases, we have 36 divided by 3. Here are our pictures. You can just sort of smush them together, and you can see that we have 3 goes into 36, and then we have a question mark here. So you could do a similar thing with 143 divided by 11. So you'll want to use your base 10 pieces, and sometimes you'll need to trade and sketch diagrams for each one of these division questions. Then finally in question 5, We're going to relate this all to our traditional paper and pencil algorithm for long division, the way that you were originally learned in elementary school. Suppose that you wish to compute 477 divided by 14. You would originally write that as 14 goes into 477. And you can see that this looks a bit like a rectangle with 14 as one dimension, 477 the actual rectangle, and then the number that we're going to put on top, the quotient, which we don't know yet, is the other dimension of the rectangle. So we're going to step through that. So in step 1, we put out our 477 base 10 pieces. Then in step 2, we're going to draw a line segment of length 14 units for one dimension of the rectangle. So that step 2 is here in this picture. Here we draw out our dimension of 14. And you can see we're going to use it in step 3 too. So step 3 says 3 sections, each of width 10, can be incorporated into the rectangle. So remember, we have 4 flats, 7 longs, and 7 units. So we can put out 3 flats, and then because we're trying to make a rectangle of dimensions 14 on this side, we're going to use 4 longs, then 4 longs, then 4 longs. So we had to trade one of our flats for 10 longs. So we have 3 plus 12. So we have 3 flats plus 12 longs, which is 3 flats plus 1 flat plus 2 longs. So we still have plenty of pieces left. And you can see how that matches the standard algorithm. Here, 14 goes into 47 3 times. And of course, this is really 3 for 30 because that's the 3 sections of width 10 across the top. Now in step 4, we keep going and we're just using all of our pieces. Remember, we still have 5 longs and 7 units. And so we can put 4 longs with units underneath, and we have to break them up. And then again, we can see that we have 14 goes into our 57 4 times, and 4 times 14 is 56. And that uses almost all of our pieces. And then finally, for step 5, we notice we just have a remainder of 1. So you can see we've made our rectangle. It's 14 on this dimension, and then here 34 across the top. So the pieces match the standard paper and pencil algorithm. So the last question that you'll do here is to draw out some rectangular arrays and show how this matches the long division algorithm. I hope you have fun with activity set 3.4. It's pretty straightforward division once you make sense of the division concepts.